Welcome to your 8-7 podcast on Pascal's Triangle. Now, before we get into Pascal's Triangle, one thing we have to review real quick are combinations. And combinations are just a selection of objects from a set when order doesn't matter. And they had this formula. So remember, n represented the total number of objects, and r represented how many we were choosing to put into a group. Okay. Now, what I want you to do on these next set of problems is just take the next about 5 minutes and do the calculation on these. Now, on one or two of them, you're going to have to decide between using a combination and another thing we talked about back last chapter, which was using a permutation to do these calculations. So take about 5 minutes, pause the podcast, and try these on your own. Okay, now that you've tried them on your own, let's kind of walk through. So if a DJ wants to select 8 songs from the top 40, okay, if he's just selecting the 8 songs, he's just choosing 8 out of 40 to put into a group. He's going to do a calculation of 40C8 to figure out how many ways he can do that. Okay, and if you calculate 40C8, that value is 76904,685. Okay, now if he was putting those into a list, either if he was making a playlist or if he was putting together a top 10 list, something like this, instead of using a combination, you would use a permutation. So 40P10. This would be where an order does matter. If there's a first, second, third, and fourth song, you use a permutation. If they're just in a group, you use a combination. So this value is much larger. 307599052400640. So notice much bigger. Okay. Now, if you're talking about a set of cards and you are given cards from a deck. Okay, we're talking about euchre here. A euchre deck only has 24 cards in them. Half are red, half are black. So if I want to know how many euchre hands are possible, I'm given the 5 cards out of the deck. So there are 24 total. So I'm going to go 24C5. Now, if you want to figure out this next probability, you need to know 2 things. How many total cards are in the deck, which we already calculated, which was 42504. But we also need to know how many hands are there that only have red cards. Okay, so let's do that next. If you want to know how many hands have red cards, well, there's 12 cards in the deck. Okay, and you're choosing 5 of them. So I'm going to start off with 12C5. That's how many hands have just red cards. Now, how many hands are there total? That would be 24C5. Do this calculation and you'll get your probability of 0.0186. Okay. Now number 4. 30 people are in a room. How many handshakes do you need to make sure everybody is greeted? Pretty much what you're doing here is you're making groups of 2 people. It takes 2 people for a handshake. And it doesn't matter who starts the handshake, so it doesn't matter the order. So what you're going to use here is a combination. You're going to go 30C2, okay, which is 435. Okay. Now, lastly, just make sure you can use that combination formula because the combination formula is going to come up again today. So if you want to calculate that combination, if I want to use the formula, 15 factorial over 15 minus 5 factorial times 5 factorial. Okay. Now, just make sure you're comfortable with these factorials now. This is 15 factorial over 10 factorial 5 factorial. Now the 15 and the 10 factorial reduce down to 15 times 14 times 13 times 12 times 11. Then the 5 factorial is just 5 times 4 times 3 times 2 times 1. And you can still cancel stuff out. So for instance, 5 times 3 is 15, so that goes away. 4 goes into 12 3 times. 2 goes into 14 7 times. So you would just have to do 7 times 13 times 3 times 11. Okay? And the answer you get is 3003. So just be comfortable filling out that formula and make sure you know that formula. Okay? Now, that's all the old stuff. Let's get into the new stuff. Now that we reviewed those combinations, what I'm going to have you guys do is take the combinations 4C0, 4C1, 4C2, 4C3, 4C4, and you can use your calculator. If you wanted to, you could use the formula. But for instance, that top row are all the possible combinations that start with 4. You can't go 4C a negative number. And you cannot go 4C5. You can't have that R value that's larger than the N value. So if you actually do these calculations, you get 1, 4, 6, 4, 1. Now, a couple of things you should notice. Some of them are just ones, and they should kind of make sense. 4C0 means you start off with 4 objects and you choose 0 of them. Well, there's only one way to do that, and that's to choose 0 of them. Similar with 4C4. You start off with 4 objects and you're choosing all 4 of them. There's only one way to do that. Now 4C1, you're starting off with 4 objects and you're choosing 1. Well, you could just choose each one and that makes up the 4. Okay, and if you have 4C3, well, that's actually a very similar question. Okay, because if you're choosing 3 of the 4 objects, what you're really doing is choosing 1 to be left out. So doing 4C3 is going to be the exact same as doing 4C1. Okay, now if you do the same thing with the 5s, you get 1, 5, 10, 10, 5, 1. Okay, so these are all the possible combinations for 4s and 5s. Now when you start doing more of them, okay, so notice here, when I start doing, there's my 4 row, there's my 5 row. But if I do all the possible combinations that start with 3s, 2s, 1s, and 0, and 6, and I stack them on top of one another, you can start seeing patterns. Like notice the first thing in every row, okay, is a 1. And then the last thing in every row is a 1. Okay, and you should notice each row is the same on the left as it is on the right. But if you take this diagram and you kind of just tilt it a little bit, you get this, which is called Pascal's triangle. Pascal's triangle is just all the possible combinations that are out there. The top row just has a 1 in it, and that's because it comes from 0, C, 0. It's the only possible combination that has n, with 0 for n, so we call that row 0. Okay, the second row, or sorry, the row 1 is made up of 2 1s, and we call it 1. That's because it comes from 1C1, or sorry, 1C0 and 1C1, so we call it row 1. Okay, row 2 comes from 2C0, 2C1, 2C2, and so on. And we just work our way down. Okay, so these numbers make up Pascal's triangle, and there are some more patterns to these, and we'll get to those patterns in just a little bit. Okay, now the formal definition for Pascal's triangle looks like, skipping ahead, this. Okay, now the one big thing to notice is that, so you can copy down this definition, N and R are non-negative integers, and to get each term you use NCR, that kind of thing. But like for instance, if you want the 5th term in a row, okay, notice what you're going to have to do. You're going to have to go NC4 because every row would start off with NC0. The second term would be NC1, the third term would be NC2, NC3, and then NC4 would be the 5th term in the row. Okay. Now, the guy who originally published and kind of discussed Pascal's triangle, or the main guy, the guy's name was Pascal. His first name was Blaise, like an American gladiator. He was born in 1623, died in 1662, and he did all of this stuff before the age of 20. So all that geometry stuff that you learn from a book, he basically helped prove. Okay, by 16, he was writing his basically own math book, and he invented his own calculator. Like a lot of mathematicians, he was also very religious. He was one of the founders of calculus, and he discovered, in quotes, Pascal's triangle. Well, to be honest, he really didn't discover Pascal's triangle, even though we name it after him, because documents like this can be found. Okay, so this is ancient Chinese, and if you take a look at it, it displays basically what we were just talking about with the combinations in a triangle, which is what Pascal's triangle really is. Okay, so what kinds of things I'm going to ask you to do with Pascal's triangle? Okay, one, you should be able to find terms of Pascal's triangle. So, for instance, here, find the first four terms of Pascal's triangle. Well, all you really need to do is use combinations. So, for instance, 10C0 would be the first term. 10C1 would be the second. 10C2 would be the third. 10C3 would be the fourth. And just do these combinations. So, like, for instance, 1, 10, 45, and 120. And you could just use your calculator to calculate those. The other things you're going to have to do with Pascal's triangles, you're going to have to look for patterns within Pascal's triangle. So I'll show you some of these patterns. Okay, and you might have been able to find some of them on your own already. Okay, first one, which we've already talked about. The first and last term of every row is 1. So NC0 and NCN are 1. Now next, what you might have noticed, if you take a look back, here's just a different picture of it. Okay, if you take a look at the diagonals, specifically like this diagonal, or you could draw the same thing the other way. It goes 1, 2, 3, 4, 5. And all of those numbers just match the row. Okay? So notice 1, 2, 3. This is the second element of this row is whatever the row number is. Okay? And the way we write that pattern is we can say this. NC1 or NCN minus 1 is always the row number n. The next one we already mentioned, and that's that each row is symmetric. It's the same on both sides. So NCR equals NCN minus R. Next, if you take a look at the sum of every row, it has a special sum. I notice it says 2 to the n, so let me show you. Okay, if you take a look at row 0, and you add up all the terms in row 0, well, there's only one term, so you get 1. Add up both terms in row 1, you get 2. Add up the 3 terms in row 2, you get 4. Add up the terms in row 3, you get 8. Add up the 5 terms in row 4, you get 16. You might guess the next one, 32. Then 64, and so on and so on and so on. The sum of the terms in each row is always a power of 2. And the last, which is probably one of the biggies. If you add any two consecutive terms, you always get the one underneath. So if you take a look, let's go back to Pascal's triangle. Notice that's always the case. 4 plus 6 is 10. 35 plus 21 is 56. That's one of the main patterns that you guys need to know about Pascal's triangle. Okay, you take any two terms and you get the one that's right beneath it. Okay. Now there are some other patterns, and these patterns go on and on and on. If you just do a Google search on Pascal's triangle, you will find pattern upon pattern upon pattern. But one more that I'll just show you that is kind of neat is what's called the hockey stick pattern. Start at any one of the ones on the sides. So I'm going to start at this one right here. And what I'm going to do is I'm going to go on the diagonal as long as you want. So I'm going to go down to that 84. Okay. If you add up these numbers, so go 1 plus 4 plus 10 plus 20 plus 35, so 50, that's 70 so far, and then add on your last two, okay? Guess what you get? That number right there. We call this the hockey stick pattern because it kind of looks like a hockey stick. Okay, but there are endless patterns to this Pascal's triangle, and this Pascal's triangle is one of the things that kind of excites me about math because it shows up in a lot of unique places. All right, so what kind of stuff am I going to ask you to do with Pascal's triangle? Or maybe a real basic proof. And this one is really pretty straightforward. So what I want to show is I want to prove that the left-hand side, or NC1 equals NCn minus 1. And actually, this was one of the properties that we just looked at, okay, where basically the second term in the list and the second to the last term in each row were both equal to n. And proving this is really easy. You just need to use the definition for combination. So what I'm going to do is I'm going to calculate NC1, which is n factorial over n minus 1 factorial times 1 factorial. Well, first of all, 1 factorial is 1. Okay, so I can get rid of that. Now, second, n factorial divided by n minus 1 factorial. They're pretty much the exact same thing except for one term, and that's the very last term. Okay, and that very last term is n. So this top thing is n times n minus 1 times n minus 2 times n minus 3 all the way down to 2n1. The bottom one is n minus 1 times n minus 2 times da 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 da, all the way down to 2n1. So what you should notice is everything cancels out except for n. So I've got NC1 equal to n so far. But now I'm going to do the same thing for NC n minus 1. Okay, so I'm going to go n factorial divided by n minus n minus 1 factorial times n minus 1 factorial. So I'm just using that definition. Okay, now this first term on the bottom looks kind of weird, but it simplifies down real nice because if you distribute the negative, you're going to have n minus n plus 1. So altogether, this term right here is the same as 1 factorial times n minus 1 factorial. So what ends up happening is if you just divide those things, it's the exact same problem as on top, and you get n. So right now, we've just proved that those two things are equal just by using the definition for combination. Okay, and the last type of thing I might ask you to do with all of this Pascal's triangle stuff is basically answer questions like these. Okay, so if you take a look at these, why don't you just take a couple minutes and see if you can answer them on your own, and then we'll kind of go over them together. Okay, so how many terms are in row 17 of Pascal's triangle? Okay, so go back and let's look for a pattern. Okay, well, notice in row 0, there's 1 term. In row 1, there's 2 terms. In row 2, there's 3 terms. In row 3, there's 4. Row 4, there's 5. So notice the number of terms, okay, in a row is always 1 more than the row number. So this will be 18. If you want the first 4 terms of Pascal's triangle and you're allowed to get your calculator in row 12, just do the combinations. Go 12C0, 12C1, 12C2, 12C3. So those terms would be 1, 12, 66 to 20. Now, the next part would actually be a no calculator question. Okay? If I give you this is part of row 7. Okay? Now, one thing that you might want to do, they want to know what the next row is, so they want row 8. Okay? So one thing you might want to do is finish off row 7. A couple of things you should know. How many terms are in row 7? Well, just like we said up here, there's 8 terms. They give me the first 5. Well, I also know the row's symmetric. So I also know the last 3 things are going to be the same as the first 3. So my last 3 terms are 21, 7, and 1. Now, if I want to get the next row, I can just use one of the other patterns. Okay, I know to get the next a row below, all I have to do is add the top 2 elements together. So 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 plus 35 is 70. This is 56 again. This is 28 again. This is 8. So I'm just using that property of Pascal's triangle. And then I also know the first and the last element of Pascal's triangle are 1s. So you can pretty easily fill out the next one. Okay, the third term of Pascal's triangle in row 10. Again, 10C0 is the first term, 10C1 is the second, 10C3 is the third. This is what I'm looking for. That would be the third term, or sorry, 10C2, I counted wrong, is the third. Okay, so calculate 10C2 and you should get 45. What's the sum of the 10th row? Okay, um, sum of the 10th row, again, we said there was a pattern if you added up all the terms of each row, and they were all powers of 2. Okay, so actually this is going to end up being 2 to the 10th. Again, just another property of Pascal's triangle. And then lastly, which rows have unique medians or middle terms? And if you think about it, it would be all of the rows that have an odd number of elements in them. Okay, so if you flip back to my Pascal's triangle on here, okay, row 0 has a middle term. Row 2 has a middle term. Row 4 has a middle term. Row 6 has a middle term. And row 8 has a middle term. Okay, so if you take a look at it, all of the, which ones have unique middle terms, are all of the even numbered rows. Okay, and right there, those are the basics of Pascal's triangle and what you're going to have to be able to do with it. I would say in terms of memorizing Pascal's triangle, I would not like memorize it down to whatever row. However, you should be able to recreate it rather quickly. Okay, using the patterns we talked about. So row 0 just has one element in it. Row 1 has 2 elements in it. They're both ones. But then if you just have those top 3, you can just use the properties of Pascal's triangle to come up with the rest of Pascal's triangle. Okay. All right, that's your 8-7 podcast. Check out the homework or try doing the homework tonight, and we will see you next time.